anyways, these kinds of systems typically do need antifreeze of some kind. We touched on this briefly with thermal energy storage and heat pumps, and there are some really simple ways of incorporating or integrating energy storage with a geothermal heat pump system, either for cooling or heating. Like I said this morning, you probably took a shower this morning, probably took advantage of energy storage. They probably had if you're staying in a hotel, probably got a fairly good sized hot water tank, and they spent half the night building that temperature up. Got a hot water tank in your house, you're using energy storage every day. And it just makes it a whole lot simpler. All you're doing is reducing the peak load. Try and supply 200,000 BTUs to heat your shower on an instantaneous basis. It's a heck of a lot easier providing 20,000 BTUs for 10 hours. A lot easier on everything. So basically, a couple different ways that I've seen energy storage incorporated with geothermal systems is either with domestic hot water tanks or with chilled water storage or ice storage tanks. The only difference between ice storage tanks and chilled water tanks is the temperatures that they operate at and how big the tank has to be. 1 pound of ice stores 144 BTUs. 1 pound of water changing 1 degree Fahrenheit is 1 BTU. And it's just a matter of volume that you're willing to, that you got space for. For domestic hot water, those loads are generally, in a lot of buildings, pretty predictable. Multifamily residential buildings, most people will take a shower between 6 and 8 in the morning or whatever time they end up going to work. Same with hospitals, they're generally pretty predictable. They know that the laundry is going to start up at the time and whatever else. And hotels, same thing. They're pretty predictable, and they're generally a very high peak, and then you got several hours until you got another peak. So if we take a look at a typical multifamily residential building, the annual cooling energy loads and peak cooling loads are greater than the peak heating loads and the peak energy load, heating energy loads. So it's a cooling dominant building to some extent. Not hugely, but a bit. And if we look at how big that ground heat exchanger has to be for this particular building, if we're looking at only the space heating and cooling, and we want the maximum temperature ground to be 85 degrees, we'll need just under 7,800 feet of drilling. And the temperature, if you look at how I know it's cooling dominant, is that the temperature doesn't get down below just under 40. So this particular building you could probably run without antifreeze. And we've topped it out. If we allow this to get up to 90, it might become a little bit more heating dominant, or not quite as cooling dominant. Shower heads you know what the flows are going to be, and you can have a decent estimate of how many minutes that shower is going to run, how many showers there are. It's not hard to multiply, find out how many BTUs you require, and if you want to supply that load on an instantaneous basis, how many BTUs per hour you'd need to meet that load. And that's basically 84 showers in a 2-hour period, 5 minutes per shower, and so on. And it's not hard to get those kinds of numbers. And you can look at, if you've got a big hot water demand, typically what's done is a water-to-water heat pump, and you can get double wall heat exchangers that are separated from the domestic water supply, so that you're separating the refrigerant from the domestic water. And you can have a couple different ways of doing it. Here we've got one larger heat pump and one tank. You can have more tanks and a smaller capacity heat pump. So there's different design approaches with that. So if we look at one approach with, let's say about 30 tons of equipment and 120 gallon tank, we've got about 310,000 BTUs capacity of heat pump installed. We're heating 1,000 pounds of water. We need a heating capacity from these heat pumps of about just under 300,000 BTUs per hour. And we could recharge that in about 20 minutes. And what happens here is that the peak load jumps up that 300,000 BTUs per hour for a couple hours. That's going to drive the size of the ground heat exchanger. So if we take the original loads that I showed you, we need 7,780 feet of drilling. Here we need almost exactly the same amount, 100 feet difference, not a big deal. And now instead of being cooling dominant, we've changed it to be a heating dominant building. All of a sudden, we've bottomed out at 32 degrees rather than going up to 85 degrees. The temperature profile of that ground loop is going to be a bit different. It's not going to get as hot, and it's going to get colder. Here we're going to need antifreeze. So the other option is looking at, instead of putting in 6 of these heat pumps, we put in two of these heat pumps, 1/3 the capacity. And instead of putting in 120 gallon tank, we put in 6 of them. All we need now is 87,000 BTUs per hour instead of 299,000. What we've done is reduce the heat extraction from the ground for a couple hours every morning and spread that over a lot more time. Because we know at nighttime there's going to be very little domestic hot water use under most circumstances. So what that does is basically take this peak load and drop it by 87,000 BTUs per hour, or down to 87,000 BTUs per hour instead of 300,000 BTUs per hour. And the only thing that we've done is change how many heat pumps we have in there and how many hot water tanks in there. We have to make sure that we've got enough capacity that we can heat up this amount of water during the time we have available, and that we'll have enough hot water to supply for the 2 hours that they needed in the morning. But what that does, because the peak load is reduced that much, this will drop this down to 6,500 feet instead of 7,800 feet. So simply by changing how we do the design of the system, the domestic hot water system, we can reduce the cost of the ground loop by, in this case, if we're 18 bucks a foot for the ground loop, about 25,000 bucks. And we're giving the client the domestic hot water. And that's compared to either doing space heating and cooling only, or the domestic hot water and just throwing a bunch of heat pump at it. The temperature range is going to be a bit bigger. It's going to go down to 32 degrees, and it's going to go up to about 83 degrees. But the loads are more balanced, and we're going to reduce the capital cost. So if we look at what the impact is on the overall system, we put in large heat pumps, small storage tanks versus large storage tanks and small heat pumps. We've got 30 tons of equipment versus 10. There's going to be lower cost on the where we've got the storage tanks. Here we're adding cost when we're adding storage tanks. We're adding about 6,000 bucks. So we're spending a bit extra here. Circulation pumps here, to meet this peak load of 30 heat pumps, we're going to need about 3 horsepower pump. Here, we've only got 10 tons of heat pump, 3/4 of a horsepower. So our pumping watts are lower. They're longer, but the peak load is lower. The ground loop circulation pumps, we'd need about 7.5 horsepower versus 5 horsepower. So slight decrease in cost here. Ground heat exchangers, where the big deal is, can reduce that by about, what is that, about 24,000 bucks. So the overall cost is lower, and you're doing more with it. If you're looking at 3 options here, this is without domestic hot water with no storage tanks, or with storage tanks. This is about the same cost as not doing the domestic hot water, just relying on the natural gas to do it. And the overall cost is actually a touch lower. And you're doing a lot more for the client. In other words, instead of paying gas, they're getting their hot water basically at a much lower cost. Where you've got time of use rates, and these are the rates in Ontario about a year or 2 back. I think they're a little bit higher now. and this is a fairly common type of scenario. And it depends on the utility a little bit and depends on what the climate is like and all that kind of thing. But in Ontario, if you're running between 7 p.m. and 7 a.m., you get much cheaper power. If you've got, on the weekends, you don't have the commercial buildings and that with the big air conditioning loads, so you get the cheaper power all weekend. And in the winter, the load shifts a little bit. Here's the on-peak time is more to meet the domestic hot water loads than the air conditioning. Here we're looking in the summer, look at the air conditioning loads, 11 a.m. and 5 p.m. Air conditioning loads, obviously, in the winter aren't as big a deal. So they shift that depending on what their peak demand, what's causing their peak demand. And typically the rates are, double for peak and about halfway between for mid-peak, and off-peak about half of what it is. In Australia, it was the most extreme I've seen, 44 cents on peak and about 15 cents off peak. So you can take advantage of that. Oregon, same kind of thing. You're looking at 13 versus 7.5 versus 4.2 cents. So it's a bit bigger of a range, but again, roughly similar time frames, winter and summer. Pardon me? Yeah. Yeah. Not all of the manufacturers produce double wall vented heat exchangers on their full condenser heat exchanger. And again, I'm not surprised that their numbers are a bit off, because to provide a same capacity on a heat exchanger, you're looking at a much bigger heat exchanger. They probably don't have room in the standard size cabinet to do that. So yeah, I'm not surprised that those numbers are off a bit. Yeah, yeah. Yeah. It's possible to make 140-degree water with some of the heat pumps. Probably not the best thing to do. Even with heat pumps that are rated at that temperature, like Climate Master makes one that will produce 140, 145. A couple of European manufacturers make them. I think Water Furnace makes one. Again, you're going to suffer on efficiency. You're probably more cost effective, or just about as efficient if you top it off with gas, heat it up to about 120 with the heat pump. Because you're looking at the temperature lift, unless you've got a very warm heat source. If your ground loop is going to be running, if you're a warmer climate, maybe you might want to consider doing that. And if you've got your ground loop that's running at 60 or 70 degrees most of the year, then yeah, you can probably get away with it. But it changes the compression ratio. It's hard on the equipment. It's probably not the best thing to do. So when we're looking at how domestic hot water use, you can predict roughly when they're going to be using it in these two areas right here, the morning or the evening, and this is the morning showers and evening laundry and stuff. That's when they're going to use it, and that's summer and winter. Here's when if you don't have the storage tanks, they're going to crank up the heat pumps and make a whole bunch of hot water fairly quickly. You're on peak or on the shoulder peaks pretty much all the time when you're doing that. If you've don't have the heat pump, if you don't install the heat pump capacity, it's going to make the hot water that quickly. Then you're going to shift a lot of that load to off-peak times. So that's going to go basically, you're spreading that load out a bit, and a lot of it's going to go into the cheaper power. Yep. From your local utility. yeah, typically if you're, you can get really detailed on it and look at what the, and said that cost, transport cost, and all the other costs that's got onto their kilowatt hour, except that peak times that kilowatt hour is going to cost you, this kilowatt hour is going to cost you. So you can get that, you can also blend the, but yeah, you've certainly got to be aware of what the rate structure is. And you can take advantage of that in a lot of cases by shifting the load. And the bigger that differential is between peak and off-peak rates, the more you can take advantage of that. In Australia, that was a no-brainer. Like it doubled the savings. So yeah, but yeah, you got to find out what the utilities are. In some places, the utilities allow a customer the option of opting in and out of the time of use rates and different smart, whether you want the smart meter or not. I suspect we're heading towards more and more time of use rates across the board. Yeah. Well, no, it's like I think you've got to allow for, if you're using a kilowatt hour, they're going to charge you that basic charge. So if your rate 12 cents plus the other one. Yeah. But yeah, that's kind of the thing. You can play games with that, but if you can try, at least if you can justify how you arrived at those, and let them prove you wrong. But if you get, and sometimes you'll get into an argument with the utility, and saying that's not the right rates to use, and well, then show me the rates that I should be using. Cooling is also generally in a lot of buildings is going to be really, really predictable. Again, two different ways, two different approaches. This is just a big chilled water storage tank. I think this is in Sacramento, if I remember right. And then this is a tank that's manufactured in New Jersey. All they do here is fill the whole tank with water, insulated tank, and then circulate chilled fluid with antifreeze through it. And the ice builds up around these little tubes. They're about half-inch diameter tubes, about an inch apart or so. This is a building about 35,000 square feet in Rapid City, South Dakota. It's been running probably about 10 years now. And we looked at the loads on there. The only thing that changes between these two charts is what this peak load is. All we've done here is top it off at a certain rate. We've topped the peak off. So in other words, instead of running for 70 tons of cooling for 3 or 4 hours, we're running 50 tons for 18 hours or whatever. It doesn't change the energy loads. That stays the same. The thing that changes is we've chopped this off and made the heat pump run more hours. Yep. You need to make sure that you've got enough heat pump capacity. Again, you've also got to that area. You've got to carry the whole way. You've got to make sure that you take enough not available. In other words, start at 8 in the morning, cut off at have a cooling load. That is they're making, got to make also, when you're making, especially in the shoulder seasons, what happens at night in a lot of places? Air temperature drop, or fucking water loss while you're filling the water storage. But more opportunity. Like this. So you can basically double the capacity or double the efficiency of the heat pump during those things. So what happened in this building is, looking at the total length of borehole we needed, dropped by about 2,300 feet, about 13%. And that's going to vary a little bit from one building to another, depending on what the loads are and a whole bunch of other things. But basically, shorter loop, same maximum temperature, more efficient in heating because the temperature is a little bit higher because you've got a shorter ground loop. So the whole thing gets a little bit better. So all we've done basically, take this electrical load here, used to run the chiller during the day, and this is where ice storage and chilled water storage tanks have traditionally been used, chop off this peak. And the only time they've traditionally been used is to reduce peak demand if there's a big demand penalty or you can't get enough power there during the day. And at the same time, they don't usually show you this kind of picture. At nighttime, a lot of times, spring and fall especially, and maybe even winter to some extent, you're going to be using the boiler, and then during the day you're going to be cooling. So what we're trying to do here as much as possible, here's what, if with traditional ice storage, chiller with ice storage, you're running the chiller at the same time you're running the boiler. What we're trying to do here as much as possible is get rid of that boiler because you've got more opportunity to heat the building. When you're making ice, you can heat the building. If you've designed your building heating distribution system to run at temperature. This is where things like the thermally activated building systems really start making more sense. Heat pumps, you can barely hear them running at those kinds of temperatures. So the numbers on this particular building, mechanical equipment was less expensive with the energy storage. Central water-to-water heat pump system, you have less tonnage, less capacity of equipment because you've got a central system. Here you've got to meet the individual peak loads of each zone. So you've got a bit more capacity. Installation, this gets a bit more complicated mechanically because your controls get more complex. Electrical to the building is reduced because you're looking at, in this particular building, is about 50 tons of equipment versus about 70. And then the earth loop is where the big deal is. Here the earth loop is more expensive than here. Saved about $75,000 bucks. Controls, they're going to get a bit more complex. Total, roughly somewhere between conventional HVAC system and this. Energy cost, because there are sometimes time of use rates and more opportunities for simultaneous heating and cooling, you should be able to get a lower energy cost. So lowering the capital cost and the energy cost, you're going to get a better payback. Yeah. At the start of the cycle, you're just barely below freezing. Store in Denver using standard 410 water-to-water. depends on how you've designed the system. But, systems that I've been first couple of days that they have to be aware of. There have been systems designed with conventional chillers where what they're doing is, because the time of use rates are there's such a difference in them, they may want to make all of the ice to run through the whole day simply with using the ice and get rid of the peak during the day altogether. So you put more ice tanks, you might even have more chiller capacity than you need. But you make as much ice as quickly as you can overnight when the electricity is really cheap, and then use that ice the next day. Depends on what your strategy is on there. What I've done so far is to keep on using the heat pumps, run them basically almost 24/7. But then at nighttime, when we don't need the cooling, we build it up and then supplement it the next day. I haven't done the system where we're doing all the cooling just with the ice, but no reason you couldn't. Yeah. The tanks that we've used so far, basically, they've said basically when the temperature is coming back to the heat pumps at 22 degrees, that's when you should stop. Simply temperature control on it. They've got ice meters on there, but they're not terribly accurate. So basically the way simultaneous heating and cooling, this is a typical central water-to-water heat pump system where it's set up so that you can either take heat from the ground loop, or you can take heat from here, and you can put heat into here, or you can put heat into here. And so we look at basically three different modes of operation. Simultaneous heating and cooling, cooling and dumping the heat on the ground, or you can reverse that and take heat from the ground and put it into the building. Where the ice storage tank fits into it is there's an extra set of diverting valves on the water side of the chilled water side of the heat pump. These heat pumps have no reversing valve in them, so we don't use it. We can either open this set of valves, or this set of valves to go to the ground loop, or this set of valves to go to the air handlers. So to make ice, you can take heat from here and dump it directly into the building, or dump it into the ground loop. So that's sort of a fairly simplified schematic of how that works. Yeah, the controls are certainly more complex. It's not probably something you want to put in a little rural scroll out in the middle of nowhere, but it's got the right kind. No question, it's going to be more complex. But in the right situation, it can big benefits to it. That particular 35,000 square foot building has the equivalent of one ice storage building. That's it applies both. Building has a cooling load of 70. Got 50 stuff. The store in Denver basically is about 400,000 square feet. Got 9 storage tanks like that. And that has a cooling capacity with the tanks themselves of about 225 tons. And the heat pumps have a capacity of about 350 tons for a total of about 575. Cooling load on the building is about 530. So if we didn't have the ice, we couldn't meet the cooling load. But there in Denver, they got a peak demand penalty of about $19 per kilowatt. Crank that up, got a much bigger peak demand. You're looking at about 0.6, 0.7, 0.8 kilowatts per ton, plus pumps. Yeah, basically all we're doing here then, when we're cooling the building with the tanks, these valves are shut so the flow can't go this way. There's a pump right here. And these valves open, and we're basically we were supplying as much chilled water as we can with the heat pumps up here. And this is drawing from here and chilling it some more and injecting back into it. Yeah. From here to here, typically those are designed with air handlers about 45 degrees or so. The chilled water storage is going to be a lot bigger, simply because ice can store 144 BTUs per pound, and without changing the temperature. Plus, you've got a bit of sensible beyond that. So let's say 150, 155 BTUs per pound. Chilled water storage, if you're running at 45 degrees, you've only got about 6 or 7 degrees to play with, and okay, and 1 BTU per pound per degree. So the tank gets a lot bigger. The efficiency of the heat pump will be a bit better when you're making chilled water, because you're not making the temperature as cold. It's going to be running at a bit higher COP. Again, you can get into the analysis a lot deeper in that, but that's basically what's driving the COP. Again, if you don't have the space for chilled water, that's not a good option. Ice storage tanks, the benefit of them is that they're relatively compact for the amount of energy you can store in there. No. There are waxes that I've seen that I'd be interested, but they're still too expensive. Mm-hmm. Yep. Again, you need very large tanks. Yep. Yeah. Oh, you pretty much have to. You can do. There are phase change materials that will melt at around 100, 110, 120. You can dial those in basically. But again, they get a lot more expensive. That's why the thermally activated building system is pretty attractive. You're building that mass anyway. And you can take advantage of that mass that's in the building. That'll help reduce the peak loads and help carry you through those peak heating and cooling requirements. You got a question? Yep. On commercial buildings, I would venture to say that the bulk of the buildings, commercial buildings, schools, office buildings, that kind of thing. Yep. No? Are they? Okay. Okay. Schools maybe not so much then. But certainly office buildings. Yeah. Just as an example, in Toronto, they've got a district lake water cooling system. They can pump, I think it's 150,000 gallons of water per minute out of the bottom of Lake Ontario through a great big heat exchanger. Some of that ends up going back to the municipal water supply. The rest dumps back into Lake Ontario. but they're taking it out of the bottom of Lake Ontario at about 39 degrees where water is most dense and cooling a whole bunch of buildings. And they've got about 75,000 tons of cooling capacity with that direct passive cooling. And even on the coldest day in January, they're doing about 20% of that load. And I got a picture just out of my office window in Winnipeg the other day. It was about minus 20 C, which is about 0 Fahrenheit. There was about 3 cooling towers I could see going at 0 degrees Fahrenheit. So don't tell me that there aren't enough cooling dominant buildings. Commercial buildings, office buildings for sure, are going to be, especially in the last 5 or 10 years as buildings have gotten more and more efficient. You've still got most of the internal gains. The lighting is getting better. Windows may be getting better, so the cooling load is dropping a bit, but you're not getting rid of the heat like you used to. Some of the old leaky old buildings dumped a lot, lost a lot of heat through the skin. You're not doing that anymore. So you're retaining all that heat, and the ventilation loads are going to be dominant. And you're doing heat recovery on that, or energy recovery on the ventilation there. Almost invariably, those kinds of buildings need 20,000 square feet. That could easily be cooling dominant. Yep. 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 If you do have a central air handling system, and again, you got to look at the whole package. What's the best for that particular building, and what an economizer package does like that for, let's say, whether any central air handling system that's supplying fresh air, or whether it's a rooftop unit with an economizer, you can get a lot of benefit from that to help you balance the loads. For example, it reduces the heat rejection to the ground if you can use the free outside air. You're not dumping as much heat. It can change the energy balance. And you can model that in something like train trace or whatever. What would be the impact of an economizer outside air directly? And using CO2 sensors, you can model that. I know you can do that in train trace for sure. Probably, I'm pretty sure you can carry a half of those things as well. There's a lot of buildings that use outside air directly for cooling the building. And you can do that anytime the air temperature is probably below about 55 degrees Fahrenheit. So instead of cooling the air mechanically with a compressor in that, you can just open the outside air damper and dump the exhaust air straight outside, and you're free cooling. And that's commonly done quite often. And that can be a good strategy, and I've used that strategy to help balance building loads. Sure. Yeah. Yeah. It's a standard hot and chilled water system. The only difference on this between this and a conventional boiler and chiller is that you're not going to get the 160-degree water that you're used to with a typical boiler. You're getting 105, 110, 120. Ideally, you should be designing, like you can design air handlers, especially with the buildings now, to heat the building with 100, 105 degree water, even in a cold climate. So basically, looking at a couple of the big benefits, basically can reduce the size and the cost of the giant heat exchanger. That's a big benefit. What I've been seeing is that the cost of the storage tanks, ice storage tanks, is roughly equivalent of the amount of reduction on the amount of the size of the heat pumps that you use. So you take out 20 tons of heat pump and you add 20 tons of cooling capacity with the ice storage, roughly a wash. And the ground would get smaller. Yes. Yeah. Yeah, typically, it's not going to work in a data center. Energy storage is not going to work in a data center. You don't have the driling. Might get some drops. Probably not. Again, it's going to I don't know enough about data centers to really speak about them intelligently. And then you can take advantage of time of use rates and can reduce construction cost as well as energy costs on the system, certainly on the size of the ground loop. And the tanks themselves, you can park them on the roof, you can park them in the parking lot, you can bury them, you can put them in the mechanic room, whatever you want. There's no moving parts really, except the water that's flowing through them. Any thoughts, questions, comments?